One of the first things you should notice on a hurricane tracking map are the horizontal and vertical lines that form a grid pattern on the map. The lines help us to pinpoint locations on the map. They represent what are called lines of longitude and latitude. Notice to the left and to the right of the map, the horizontal lines are labeled. Starting with 10 degrees at the bottom of our map, we count up 5 horizontal lines to 15 degrees, that is 15 degrees north, and another 5 lines to 20 degrees north. Each of these horizontal lines will correspond to the northerly part of our coordinates. Across the top and bottom of the map, the line furthest to the right is labeled 50 degrees, and the numbers count up by 5 as we move in a westerly direction. So we have 50 degrees west, and then 55 degrees west, and 5 more lines away is 60 degrees west. Coordinates are a way of describing where on the map something is located. By identifying which horizontal plane it is on and which vertical plane it is on, we can find the exact location of a point. For example, the coordinates of A are 12 degrees north, 54 degrees west. That means the point A is somewhere along the 12-degree north line. That line is 2 lines up from 10 degrees north, so somewhere along this line. It is at the same time somewhere along the 54-degree west line, the vertical line just before 55 degrees west. So just before 55 degrees is 54, somewhere along this line is where we find point A. And there's only one place where the point can be both on the 12-degree north line and the 54-degree west line, and that is at the point where they cross or intersect, and that point is the location of A. Similarly, point B, located 15 degrees north, 60.5 degrees west, is along the 15-degree north line, but also on the 60.5 degree west line. Now our map has a 60-degree west line and a 61-degree west line. So 60.5 degrees west would be halfway between the 60 and 61-degree line. And again, where the lines intersect is the location of point B. A third example, point C, 18.2 degrees north, 57.9 degrees west. For coordinate values with decimals, we will have to give our best estimation. We know 18.2 degrees is just a bit further north than 18 degrees, so we trace our line just above the 18-degree north line. And again, 57.9 degrees is just shy of 58 degrees, so we trace our line close to the 58-degree line but not on it, just before it. And where the two lines intersect, that is the location of C. Now let's take a look at an example of using hurricane tracking and reading the map as we have it. Hurricane Tina was located at 11 degrees north and 51 degrees west at 6 a.m. on July 21st. By 10 a.m. on July 22nd, she was positioned at 13 degrees north and 56 degrees west. Hurricane force winds extend 100 kilometers in all directions from the center, that is the eye of the hurricane. On the map provided, use a scale of 1 centimeter to represent 100 kilometers. The first thing we are asked to do is plot the locations of the hurricane on the 2 different occasions, and after that we are asked to draw circles representing the hurricane and show the expected path. The July 21st location is 11 degrees north, 51 degrees west. One line up from 10 degrees north is 11 degrees north, and one line across from 50 degrees west is 51 degrees west. And that's our first point. The second location is 13 degrees north, 56 degrees west. Tracing our lines, we are able to plot this point at its location on the map as well. The points represent the center or the eye of the hurricane, and the wind of the hurricane reaches as far as 100 kilometers in all directions. A circle that has a radius of 100 kilometers would best represent our hurricane, but of course we cannot draw a 100-kilometer radius circle on our map, so we use a scale where 1 centimeter represents 100 kilometers. So our two circles should have a radius of 1 centimeter to represent 100 kilometers in reality. Thirdly, assuming the hurricane continues in a straight line northwesterly direction, the path of the hurricane can be shown with two parallel lines tangent to the circles and extended into the Caribbean. We are now asked to identify the countries directly hit by the hurricane and those impacted by stormy conditions. We must also calculate the speed at which this hurricane is traveling. Any land that is between the two path lines that we've drawn will be hit directly by this hurricane, while the territories or the islands on the outskirts of these lines, very close but on the outside, those are the ones who will experience stormy conditions. Islands very far away will not experience any kind of effect from this hurricane. So islands like Martinique and Dominica will be directly impacted by this hurricane, and places like Barbados, St. Lucia and Guadeloupe will experience stormy conditions. To calculate speed, we need to know the distance traveled and the time taken. The time taken we can derive from the information provided in the question, but the distance traveled we will have to get from our map by measuring. Well, we will measure in centimeters the distance from center to center of the two locations that we have drawn for our hurricane. In this case, our measurement is 6.7 centimeters. So our formula says speed equals distance divided by time. Using the scale 1 centimeter on the map is equal to or represents 100 kilometers in reality, we can translate our measured distance into a real distance by multiplying by 100. The distance the hurricane has traveled is 670 kilometers. As for the time taken is from July 21st 6 a.m. to July 22nd 10 a.m. July 21st 6 a.m. to July 22nd 6 a.m. would be one full day, 24 hours. But then there's another 4 hours to go from 6 a.m. on the 22nd to 10 a.m. on the 22nd, which altogether gives us a length of time of 28 hours. 24 plus 4 is 28 hours. Therefore, the speed of our hurricane is 670 kilometers divided by 28 hours, which equals 23.9 kilometers per hour.